The question now becomes, how do we introduce that carrying capacity to our differential equations model? So this is how it's going to look. We're going to start off lower down, and the rate at which our population is increasing will be increasing for a while. And then at some point, the rate is going to get smaller, and it's going to level off. Notice that the population continues to increase, right? We're not losing population, we're just gaining population at a slower rate. So the rate of change is what I'm saying starts out positive and changes to negative. We're going to approach some sort of carrying capacity. One of the important characteristics of logistic growth is that the maximum growth rate will occur when the population reaches exactly 1/2 of the carrying capacity. So if our revisited population of birds has a carrying capacity based on this graph, we should be able to look at the graph and see what that carrying capacity might be, at least approximately. And we can see that there might be this horizontal asymptote at a population of 700. Maybe it's not exactly 700, but sure, let's call it 700. So the carrying capacity appears to be 700 birds. And that means that our population cannot exceed 700 birds because the system can't accommodate more than 700 birds. Okay? So we know of that because of the horizontal asymptote. At what year will the rate of population growth change from increasing to decreasing? Okay, well, let's see. The carrying capacity is 700. So we are saying that we'll reach 1/2 the population at the point when we're changing our rate of growth. So half of 700 is 350. 350 is right here. So round about right here, boom, that is the point in time when we change from a concave up to a concave down graph, a positive rate versus a negative rate of population growth. So if the question is what year will that happen, then we just read on the graph down to here and we see that that happens at t = 8 years. Okay. We know that that's when that maximum rate of growth happens. So if we want to approximate that maximum rate of growth, we want to approximate dt, in other words, the slope of this curve right here. And it sure does seem like we're going up 1 and over 1, but pay attention to the units. This is going over 1 to 9, but it's going up from 350 to 400. So this is actually going to be an increase of 50 birds per 1 year. That's the fastest rate of growth that we're going to see in this logistic model. So our rate of growth is going to start out over here at something less than 50 birds per year, and our rate of growth is going to get bigger and bigger and bigger. As we get more birds, we get more birds making more birds, right? But then we've hit that critical point of inflection right there where we don't start losing birds, we stop gaining birds at a faster rate, and we're gaining birds at a slower rate after that. Okay, so these two different models are both very common population growth models. We've seen the exponential growth, that's dp dt is directly proportional to p, and we've solved that to be the population equals c times e to the kt. When we look at logistic growth, notice that we still have that kp in the mix, but we also have this 1 minus p over l, and that's kind of important. That extra piece is what's going to introduce this carrying capacity line right here. And we're going to come back to this equation in a moment, but I thought it might be nice to include that in one big box right here. So this is the general solution to an exponential growth. Over here, this is the general solution for a logistic growth model. Okay, so let's talk a little bit more about the differential equation itself and why it provides that logistic growth shape. Okay, so back in the days when we were looking at exponential growth, remember that was dp dt is directly proportional to the population. We saw that dp dt equals 0 only when p equals 0. If p equals any other value, then our rate of change is going to be non-zero. And if the population is positive, then the population growth is positive, and it will just continue to get bigger and bigger and bigger because of exponential growth. This, of course, I guess, assumes that k is positive. Right? If k is negative, then we have exponential decay. But we're assuming that we're gaining population in this problem. So remember, the big difference here in the logistic differential equation is the addition of this new factor. We're multiplying by 1 minus p over L. So if I ask the same question, when does this equal 0 versus when does that equal 0? If I ask the question about the differential equation, I've got two different factors. I've got kp equals 0, but I also have 1 minus p over L equals 0. Solving for p here, I'm going to get p equals 0, same as before. But if I solve for p here, I'll add the fraction to the other side and multiply both sides by L, and we're going to find that when p equals L, our carrying capacity, then our differential equation is going to equal 0 again. So what that's telling us is we don't have just one horizontal asymptote on our graph, we have two. One of our horizontal asymptotes is at p equals 0, and the other one is at p equals L. And we can see that here. Here is L. That's a horizontal tangent line right there. And here is 0, and we've got our horizontal tangent line right there. Notice that we do not have that dual horizontal asymptote over here. We just have that single horizontal asymptote at 0. And going back up to that original example, we can see that L happens to equal 700 in this example. Okie dokie. Okay. So we can solve the differential equation for the logistic model. However, it requires partial fraction decomposition, and that's a Chapter 8 question, and we're only in Chapter 6 right now, so we can prove this later. But for now, just accept that other people have figured this out, and the differential equation can be solved, and we'll look at this as the general solution to a logistic problem. Okay? L, of course, is the carrying capacity. B is related to the constant of integration. K is this same K value here. E, of course, is Euler's constant 2.7 or so. T is time, P is population, and it becomes an equation that we're going to want to become familiar with. Alrighty, so one more thing to consider before I jump into a few examples in the next video is I want to try to convince you about this fact that, that the rate of growth is going to reach a maximum halfway between 0 and the carrying capacity, exactly halfway between 0 and L. And to do that, we're going to consider a simple differential equation where K and L are both equal to 1. So if I replace K with 1 and I replace L with 1, I get this simple logistic differential equation, P minus P squared. Okay? And we don't normally do this, but we could certainly graph dp dt as a function of p. So we've got a p-axis, and we have a dp dt axis. And it shouldn't be surprising, since we have taken algebra in the past. We know that the function y equals x minus x squared is an upside-down parabola. So this is what we're talking about right here, right? We've got an upside-down parabola whose intercepts are at 0 and at 1. All right, and not only that, but we know that parabolas are nice and symmetrical, so we know that if we're increasing at the first x-intercept, we're going to hit some sort of maximum point. When we start decreasing, we're going to go back down to the second intercept, and that maximum point is always going to happen exactly halfway in between the two intercepts. We can, in fact, prove that using the first derivative test. But we're already fairly familiar with the symmetrical properties of parabolas, so I don't think we need to go into too much detail with that. But at any rate, we'll notice that this special value right here is exactly halfway between 0 and 1. This is at 1/2, exactly halfway between 0 and the carrying capacity. And that's why we're reaching a maximum rate of change. Remember that dp dt is measuring the rate of change of the population, so that rate of change get as big as possible when we hit that, that vertex of the parabola. All right, so on the next video, we'll take a look at some numerical examples that involve the logistic differential equation.